This time we're going to discuss about Xenon compounds, more specifically the part in the NCERT, starting from Nonfluorine compounds till the end of the chapter here. So we'll study about Nonfluorine compounds, that is very obvious, and then hydrolysis reactions. It was actually very hard for me to do it, but eventually I found out a way to do it. Structures, very frequent questions, and lastly reactions with fluorine acceptors and donors. Starting with Nonfluorine compounds, here we see that Xenon forms three binary compounds, three binary fluorides. Why binary? Because it has only two elements, xenon and fluorine. Later on we see compounds which have three elements, that's why they're no longer binary. So when you talk about binary fluorides, there are only three: XeF2, XeF4, and XeF6. In the NCERT, there are only two methods of preparation. There's only one method of preparation each for XeF2 and XeF4, but they've given two methods of preparation for XeF6, which we're going to discuss. Before we go into the preparation methods, we'll do some physical characteristics of XeF2 and XeF4. I'll do it directly from the textbook. So the first point is they are colorless crystalline solids, nothing special, not important. Next is they're readily sublime at 298 Kelvin, which is kind of a point to remember, that they're readily sublime and they do it at room temperature. They are powerful fluorinating agents. And lastly and most importantly, they are readily hydrolyzed even by traces of water, so they very, very easily undergo hydrolysis reactions, which we'll discuss here. And so in total 4 points are important to remember here. Colorless crystalline solids, sublime readily fluorinating agents, and hydrolyzed even by traces of water. Coming back to the preparation. So obviously all of these can be prepared by direct methods of preparation, but you need appropriate conditions to get the product. In this case, for XeF2, the conditions are 673 Kelvin temperature, 1 bar pressure. Here it is 873 Kelvin temperature, 7 bar pressure. Here it is 573 Kelvin temperature and 60 to 70 bar pressure. In all these cases, the reactants are in gaseous phase here and here, but the products are in solid phase. That is a point given here. Moving on. The second method for preparation of XeF6 is by using a compound O2F2, which is basically an oxygen fluoride. And if you remember properly, we studied about this compound in the chapter of halogens. So I'm going to quickly revise that part from the halogen chapter, from the part where they talk about reactivity towards oxygen. So they typically mention two oxygen fluorides. One is OF2 and the other one is O2F2, and we have to remember distinctive points, one each, about both the fluorides. For OF2, we have to remember that it's thermally stable at room temperature, and out of the two, it is important to know which is thermally stable. Instead of room temperature, you can also say to 98 Kelvin. For O2F2, we have to know that it oxidizes plutonium to plutonium hexafluoride. Now this happens, so that's why it removes plutonium as POF6 from spent nuclear fuel. That's how it is used. Similar to these three fluorides, even these two are strong fluorinating agents, again, which is mentioned here. And that's all that is mentioned in reactivity towards oxygen involving fluorine. So that's what I wanted to quickly revise. Now coming back to the topic we were discussing, preparation. So when you're preparing XeF6 from O2F2, you use XeF4. So this is definitely not a direct reaction. You get XeF6 and O2. So this is an alternate method for preparation of XeF6. Now that is that. So as we discussed, all these three easily hydrolyzed by human traces of water, that leads us to do hydrolysis reactions. So let's do that. So there is one reaction given for XCF2 and there is one reaction given for XCF4, but there are three reactions given for XCF6. So in all these reactions, let me just write down the products which are common. The only other product we use is water, obviously. So let me just write it down quickly. Sorry for the delay. I should have written down before, I know. Yeah. So the point that I really wanted to let you all know, which made it so much easier for me to remember the products, is that there's one product that is common to all 5 reactions. That is HF. HF is common to all 5 of the reactions. That clears a lot of confusions. And the number of molecules of HF is twice the number of molecules of water or H2O. That is very, very basic. Now, the other products of the first reaction, that is of XCF2, are Xenon and oxygen. These two are common for this reaction too. But there's one distinctive product in this reaction which turns out to be XeO3. That's the only thing that is different between these two reactions, that is XeO3. If you do the addition subtraction well, you can actually find it out. But moving on, that's done for the first two reactions. I'm talking about these three reactions. So here you use 1 water molecule, here you use 2, and here you use 3 water molecules. So these two reactions are partial hydrolysis, as mentioned here, partial. But this one is complete hydrolysis. So for 1 water molecule, 2 HF, here 4 HF, and here 6 HF. Now what are left to do is that subtract or just balance the elements on both sides, so you'll get the other product, because there are only 2 products in all the 3 reactions. So when you balance out, here you get XeOF4. That's what you get here. Here you get XeO2F2, and here you get XeO3. So it's very simple. You don't even have to remember. You can just find it out on the spot. So those were the hydrolysis reactions. Moving on to the structures. So it's very actually simple. It's mentioned here that the structure of the 3 Xenon fluoride can be reduced by VSEPR. XCF2 has a linear structure. You have F here and F here, and 3 lone pairs. And then XCF4 has a square planar structure. So you have a square here. This is a square, and then you have lone pairs. And then we come to XCF6. Here it is given, very important thing, that has 7 electron pairs and would thus have a distorted octahedral structure as found experimentally in the gas phase. That is also a point that is given. This is the distorted octahedral. Just you have to know it. The more times you watch the video, more times you revise the textbook, that you'll just automatically remember these things. Next structure is of XeOF4. Simply to this structure, instead of adding a lone pair on the top, you add an oxygen double bond. That'll give you XeOF4. And then lastly you have XeO3, just 3 double bonds and 1 lone pair, which is here, pyramidal. XCO3 is a colorless explosive solid and has a pyramidal molecular structure. XCO4 is a colorless volatile liquid, has a square pyramidal molecular structure. Again, the more times you revise it, the more easily you remember it. So that's done for hydrolysis and structures and preparation. The only thing left is this part, and it's very simple, basic. So when xenon fluorides react with fluoride acceptors, okay, so you're taking a xenon fluoride as given here XCF2, you're reacting it with a fluoride ion acceptor like PF5, so you will get a cationic species which is XCF plus, because PF5 accepts a fluoride ion to give PF6 minus. So here you're getting a cationic species. But if your xenon fluoride reacts with a fluoride ion donor, so for example a metal fluoride, the metal can be any alkali metal, which is sodium, potassium, rubidium, cesium, as given here, then you'll get a fluoroanion, which is XCF7 minus and the metal ion. So you get a fluoroanion, don't mind the spelling. So when you react as a non-fluorides with fluorine acceptors, you get cation. When you react them with donors, you get fluoroanions, which is pretty basic, I think. That's all for this video. Thanks for watching.